Okay, welcome back everyone. Hope you had a good weekend. So last time we were talking about a few important things we can learn from geometry of these linear classifier problems. So here we have a picture in 2 dimensions, which is easy to visualize, where we have some red, some data points from the red class here, data points from the blue class, and so a good linear classifier would have this boundary here. And so one thing we started to remember is that basically the way linear classification works, it's like a 2-step process. In the first step, you compute the score, which we call z, which is this quantity, the bias plus the inner product between the test feature vector x and the weights w. And one thing we know is that when a point is right on the boundary, that score will be 0. So that gives us a way to mathematically describe the boundary as a set of feature vectors x that give you a score of 0. And then the next thing we said is, we basically deduced that the weight vector w is going to be perpendicular to that boundary in all cases. And we did this by picking any 2 points on the boundary and looking at the 2 different score equations we get from them, both equaling 0, subtracting them, and that shows us that basically the vector between those 2 points, which is going to be on the boundary, on that separating hyperplane, is orthogonal to the weight vector. So that's the next thing we talked about. Then we said, let's take any point like this one, xi. We said that basically the farther this point is from the boundary, the easier it is to classify. So basically, like the points closest to the boundary are going to be the most difficult, especially if you have a point really close to the boundary. Because our data has a bit of noise in it, it's really hard to know whether that point should be on one or the other side of the boundary. However, a point that's far from the boundary like this one is pretty obviously in the red class. So as one way to sort of describe the difficulty of a point for classification, we could look at the distance from that point to the boundary. And we're going to formulate a particular kind of distance that's signed, because usually distance is just a non-negative quantity, but this is a signed distance, which takes into account the sign of z. So z, when you're in class 1, remember that z is positive. So if the weight vector is pointing this way, then these would be the class 1 points, and these would be the class -1 or 0 points. So what we said is we can figure out the signed distance to a boundary by taking any point and basically moving in the direction of w, and then figuring out how we need to scale that movement. So what we did is we came up with a unit norm version of w, where we took w divided by its norm. So that's a direction vector in the direction of w. And then we said, let's tack that direction vector onto our point xi, but now let's multiply that by a real number gamma and figure out which gamma we need to put it on the boundary. So maybe in this case, we need a negative gamma that will bring us all the way to this point on the boundary here. And basically we said, here is the point. This is where we are after we move. So this is our xi. Let's see, Okay, so this is our xi. This is moving in that direction. And if we've moved the point so that it's on the boundary, it should satisfy this equation here where we equal 0. So then we can just basically solve this equation for gamma I, after which you get this here. So this tells you the sign distance from the point xi to the boundary. So if you want to move to the boundary, this is how we define that sign distance. And we're going to be using this to develop our support vector classifier, which we're going to talk about later today. Okay, any question on this last point? This is pretty important. Is that making sense? Okay, and then the last thing we noticed is that if we start with a classifier parameterized by b and w, and what you do is you scale both b and w by the same positive number alpha. When you look at the intercepts, you can see that the alpha will cancel in the numerator and denominator. You'll have exactly the same intercepts, meaning you'll have exactly the same boundary. So if you're given a b and w, you can actually scale those two things by the same number, and the boundary won't change. What does change, as you can see from this equation, if you scale b and w together, you'll change the sign of z for a given x. So let's say you scale b and w to like 100 times the previous values, then z will be 100 times larger than it was. And if you remember, z is sort of like a confidence in classification, and it relates, if we're doing, for example, logistic regression, then we know that the probability to be in class 1 is this number. So you can see how z affects that, the size of z will affect that probability. But in any case, so this is the last thing we talked about, this equivalence idea. Now we do have to be careful about the sign of alpha, because here you can see that if we multiply b and w, let's say by -1, then we'll have the same boundary, but the sign on z will change, and that means that when we, remember basically what we do is we quantize z, we look at if z is greater or equal to 0, then we choose y equals 1. So here you can see if we flip the sign on z, that means we would flip our decisions between the positive and negative class. So this is why we only want to consider positive scalings, otherwise we'd actually flip like, where the red and blue points, on what side of the classifier boundary they lie. Okay, so those are sort of the setup for what we're going to do next. So any last questions on any of this? Okay, all right, so now let's also come back to linear separability, which is something we talked about, but we're going to try to make it a little bit more precise today. So, so from a visual perspective, we say that a training data set is linearly separable if you can find some boundary for which all points in one of the classes is in one side and all points in the other class is on the other side of the boundary. So this would be an example of a linearly separable data set. And an example of a data set that's not linearly separable is if I put one of those square points over here, then there's no way I can find a boundary that has all the circle points on one side and the square points on the other side. Okay, but anyway, this is going to be one linearly separable data set. And now you can see that there's actually many boundaries that are going to separate those two classes. There's not just one, right? Okay, so that's sort of intuitive notion of linearly separable. So now let's try to make it a bit more mathematical. And to make the notation easier, we're going to assume that the y's are, the yi's are plus minus 1. You can do everything for general y, but it's just that the notation gets more complicated. So we're going to do this just to make it simpler to describe. Okay, so let's start with maybe the most obvious mathematical definition of linearly separable. It goes like this. So if there exists some b and w and some positive number epsilon, okay, such that b plus xi transpose w is greater or equal to epsilon whenever yi is 1, and b plus xi transpose w is less than epsilon. Now remember that this quantity we're talking about here, this is like zi. So from the perspective of the score, maybe it's easier. Whenever that score for the ith sample is greater or equal to some positive epsilon, whenever that happens for all the 1 labeled points, and whenever the score is negative for all the -1 labeled points, then we have this linearly separable idea. Is that making sense? Okay. So, so another way we can, so this definition is fine, except that it's kind of complicated. There's 3 parameters. There's b, w, epsilon, and there's actually 2 different inequalities. So maybe we can simplify things a bit. So as of the first simplification, if y is plus or minus 1, then notice that if we multiply both sides of these inequalities by yi, let's see what happens. So if I multiply the left side by yi here, in this case, yi is 1, so the right side doesn't change, right? It just stays epsilon. But if I multiply the left side over here by yi, then because yi is negative in this case, I have to flip the sign on the inequality. Oh, actually, I made a mistake. There should be a minus over here on this epsilon. Sorry about that. Okay, so here we want the score to be, greater or equal to some positive number, and here we want the score to be less than or equal to some negative number. Okay, so now coming back to that second idea, if I multiply by yi here, I have to flip the sign because yi is -1, and then I can also kill that minus because yi is -1. And at that point, you can see that actually both sides have exactly the same form. So I can rewrite those 2 inequalities as a single one. So this is nicer because instead of 2 inequalities, we can just focus on 1. Okay, so we need that this happens for all I in the training data set. If you want to think about this as the score, and this you can say is like, because y is plus or minus 1, this is like you're correcting the sign on the score. And if this sign corrected score is always positive, that's what it means to be linearly separable. So like, for the yi equals 1 class, the zi's are positive, you multiply them by 1. And then for the y equals -1 class, zi's are negative, but you correct that negative with a -1, and then the sign corrected zi's are positive. Okay, so that's an improvement. Any questions on this one? So far, so good? Okay. So now we can make one other simplification. Let's say that we divide both sides of this equation by epsilon. So then I get 1. I'll put an epsilon there, and I'll put an epsilon here. So now it basically looks like I have the score again, but for a new bias, which is b over epsilon, and a new weight vector, which is w over epsilon. And remember that if we scale b and w together by the same positive number, that is basically giving us an equivalent classifier. The boundary is identical, right? So essentially it's just a new classifier with the same boundary, but a slightly different scaling on the score. And so basically that means that if you can find some b, w, and epsilon for which this works, then you can also find some b and w for which this works. And what's nice about this is the epsilon is now gone. We don't have to worry about it. It's kind of like saying if you can find a B and W that works for epsilon, then you can always scale them to work with epsilon equals 1. And this is going to be our final definition for linear separability moving forward. So this is a nice compact way to think about linear separability. So again, we have our score for the ith sample. We correct the sign on that score by the label, and we find that it's greater or equal to 1 for all samples in our data set. Okay. We just need to be able to find some B and W for which this works, and then we have a linearly separable data set. Yes?
This might be kind of a dumb question, but why don't we scale X by epsilon?
Well, if we're dividing both sides by epsilon, we just want to do this, right? This wouldn't be correct. I don't know if that answers. This is like epsilon dividing by epsilon squared. Okay. Okay, so yeah, so this is our new definition of linearly separable. Okay, so this is important. We're going to be seeing a lot of this equation. So any questions on this equation or inequality? Okay. And the last step is to remember that on the previous slide, we have this definition for the sign distance to the boundary. So from this, you can, if you wanted, we could like move the norm of W to the left side. And we can then take this equation and plug this in to our linear separability to rewrite that B plus xi transpose W in terms of gamma I norm of W. So if you replace this with gamma I times norm of W, and then you divide both sides by norm of W, you get this equation. So here you have your yi gamma I on the left, and on the right you have 1 over the norm of W. Okay, so if you have a linearly separable data set, then there exists some weight vector such that this sign-corrected signed distance for all the points is greater or equal to this number 1 over the norm of W. So this is an important quantity, 1 over norm of W, and so we're going to give it the name of gamma, and we're going to call it the margin. So the margin gamma is just defined as 1 over the norm of W. Okay, so let's think more about, or maybe try to visualize what this is saying. So this says, if you look at this signed distance for all the points I, and then you correct that signed distance, multiplying by, either 1 or minus 1, that thing is greater or equal to some number. It's lower bounded by some number for all the samples. So here we have a picture of this. So we have our points, squares, circles. And what we're basically saying is that, okay, maybe these are all positive distance and then these are all negative distance. But if you sort of correct or, change the sign on all the negative distances, basically it's saying that all the points are at least a distance of gamma or a distance of 1 over norm of W from the boundary. So it basically means that there's this is the picture of gamma here. That would be gamma, and then this would also be gamma. So gamma is a lower bound on how far all these points are from the boundary. That is the meaning of the margin. So do we want that lower bound to be small or large? What do you think? Do we want gamma to be small or large? Large, right? Because the bigger this space between the two classes is, the more robust we're going to be. This is our training data here. So our test data is not going to be exactly like our training data, but it should be similar. So if the training data all looks like this, then maybe the test data shouldn't look too different. Maybe the test data has a few points that are a little bit more difficult, closer to the boundary. This margin gives us sort of a bit of wiggle room. It gives us like some insurance that we probably won't make a test error because there's a lot of space to the boundary. So that's what we would like. We would like to have maximum margin. We'd like to find a W with maximum margin. Let's try to picture what happens if I change the W in this picture. Like I could, for example, I could make W like this. This is still linearly separating the data, right? But notice what happened to the margin. It got a lot skinnier. So this classifier works just as well for the training data in that it classifies everything perfectly, but it might not work as well for test data. Maybe I have a test data point here, a circle, that is going to violate that classifier. So that's why we want to make sure that we position our classifier just so that basically like the minimum distance to the closest point is maximized. So that's sort of the philosophy behind what we're doing, or part of what we're doing in this unit. Yes?
So when choosing your classifier, would you always choose the classifier with the maximum gamma?
That's going to be the philosophy that we're going to use on the next slide. Exactly that. That's a different philosophy than what we've used so far, right? So far we said, like, let's define logistic loss. Let's, minimize this logistic loss and stuff. And we were content with that because that was like working for us to some extent. But now we're basically saying like we can look at this a different way, and we could try to maybe design a classifier that's more robust.
So how do you handle the data that falls within W?
So how do we handle data that is not linearly separable, or?
Yeah,
Okay.
within W. So
Well, W is a weight vector. So this is just showing you the direction W is pointing. So do you mean like points in this region?
yeah,
Okay, well, there can't be any points in that region because the region is defined such that it doesn't include any points. So if there was a square here, we would just have to redefine our region to be like that, and that would be our new region. And that would have a smaller margin, and we would be a little worried because that's less robust than this. This has more robustness, has a bigger, if we call this the street, it has a wider street. Yeah. Okay, so is it starting to sort of make sense? So the margin is like a lower bound on the minimum distance from any training point to the boundary. And essentially, we want to do something like maximize the margin as our classifier design approach. Okay, so let's try that. So to make this classifier robust, let's maximize the margin. And so this whole margin thing here only makes sense when the data is linearly separable. If the data is not linearly separable, well, we don't actually really know how to proceed because all of this is based on linear separability. So let's just move ahead for now, saying that the data is linearly separable. So what I could do is I could formulate the design problem like this. I'm going to find the B and W that minimize one half of the norm of W squared. Remember, that is going to be like the squared inverse margin, such that the linear separability condition is satisfied. Okay, so here we have basically 1 over gamma squared. The reason we're including the square on here is just because the math works out easier. If you minimize the square of something, that's equivalent to minimizing it without the square. But as we know, the Euclidean norm squared is nice. It's just the sum of the squares of the components. Okay, so here we're trying to minimize like the inverse squared margin, which is going to maximize the margin. And then this is the very important linearly separable constraint. So when we have this happening, then this whole margin thing makes sense. Then we really are minimizing the gap between the two classes of data. Okay, so this thing is going to be called the hard margin classifier. So if you look at all the designs B and W that give you linear separability, so like as we said, you could imagine maybe some other ones that separate the data, they're going to give you streets that are not as wide as the hard margin classifier. The hard margin classifier is going to wiggle around the boundary until it gives you the widest possible street. So visually, like if you see a homework problem where you have just visually a bunch of data points, it's pretty straightforward to draw that boundary visually, right? You just kind of figure out where you need to put the line so that you have maximized the minimum distance to both classes of data. And once you have that line, if you needed to figure out what are the B and W, you can look at the intercepts that you get and then figure them out that way. Now, there is one sort of catch if you think about doing that. It has to do with the scaling on W. So if you imagine all the W and B's that give you exactly this boundary, remember there's many of them because when you look at the intercepts, you have things like this, which means that as you scale B and W together, the intercepts don't change, right? So I could scale W and B together, and this part won't change, still be linearly separable, but as I scale W, this part does change. So, yeah, so essentially there's some sort of balance between both the sort of the angle, the position of the linearly separating hyperplane, as well as the actual coefficients that try to maximize or actually minimize this term here. Okay, so, all right, so is this hard margin classifier sort of making sense? So we're maximizing the margin subject to linear separability. Okay. So now when you look at this results, you notice something pretty interesting, that this boundary, at least in this picture, is completely determined by these three data points, right? If I move any of these other ones around, the boundary doesn't change. So really, the boundary is now all about the few training points that are the ones that are most difficult to classify. So that's something that's, again, different than what we did before with logistic regression, where we really did use all the training points. And it was also something that we talked about maybe as a motivation when we were looking at those MNIST digits. We were saying, like, maybe one of the issues with logistic regression is that it's sort of getting distracted by some of these easy to classify points and not spending as much time on the difficult to classify points in our training data set. Okay, so these few points that determine the boundary are called the support vectors. So they're the few elements of your training data set that actually determine that boundary. So in this case, there would be three support vectors. It would be those two black points and the one white point. All right. So what are your questions here? Any questions? Okay. Is it making sense so far? Okay. So there is an issue with this hard margin classifier, is that it's pretty restricted because it requires this linear separability to be satisfied. So if I have a data set which has, let's say, a solid point over here, I can't apply this idea because there exists no B and W such that that happens. So this is the right idea, but unfortunately it's just a bit too limited to use in most practical situations. So the next thing we're going to do is we're going to come up with a different way of formulating it that is a bit more generic, that still does this when the data is linearly separable, but can also handle data that is not linearly separable. All right. Before we go on, are there any questions on anything here? Okay. So this is how we're going to handle this data that is not linearly separable. So let's think again what our constraint was. Our constraint for linear separability was basically yi times b plus, actually we wrote it xi transpose w must be greater or equal to 1 for all I. So notice that if I have that inequality, I can subtract this term on the left from both sides, and I can equivalently write that as 0 greater or equal to 1 minus yi of b plus xi transpose w for all I. Right? These are just two ways of saying the same thing. Okay, so if we have linearly separable data, it means that this thing on the right is at most 0, no larger than 0. In most cases, it's going to be negative. Okay, so what we're going to do is we're going to replace this hard constraint with this cost. And so our cost is going to be the sum over our data points of the max of two numbers. So this is it's whichever one of these two numbers is larger, that's what the max will return. It either returns 0 if 0 is larger than this, or if the second one is larger than 0, it returns that number. So is it clear what we mean by this? This is not like, this is basically just maximizing between those two alternatives. So, okay, so now you can see, like, if we can find a B and W such that this hard constraint is satisfied, that means that this number here is at most 0, usually less. That means when you take this max, the max will always be 0, right? Because it's 0 or something that's at most 0, or usually less. So that means that if you do have linearly separable data and you find that hard margin classifier, it will actually give you a cost of 0. But if you have data that is not linearly separable, it's not like everything falls apart. It means you won't be able to drive this cost all the way to 0. However, you can drive it to 0, or you can drive it close to 0. You can maybe set it to 0 for most of your samples, but maybe just not for those few that can't be linearly separated. Okay, so basically what we're going to do is we're going to take this old optimization problem, and rather than this, minimize this such that this holds, we'll minimize this plus a cost term. And that cost term is this. Okay, so here we are. Here's that first part. Minimize B and W of 1/2 norm of W squared, which is like the inverse margin squared. And then here is that cost term. Now, the only thing that's new is that we've also snuck in a number C, which is going to be a tunable weight that's always going to be positive. And that's because it's not really clear exactly how we should weight these two terms. Basically, when we minimize the sum of them, the value of C will tell us how much emphasis to place on the first one compared to the second one. So if C is really large, that means that this thing is really important, and this term is not as important. Meanwhile, if C is really small, it means that this term is important, and this term is not that important, right? Because it's going to be minimizing the sum. And so basically, if C is large, it means that you really don't want to have any, what I call, violations in the margin. You don't want to have any of this stuff happening. And this will basically, in some sense, like if the data is linearly separable, this just sort of measures how many times do you violate this. Right? And so if C is large, you'll be able to squash that down to 0, at which point you'll be satisfying this constraint, but then minimizing what remains. That's what happens if C is large. Now, if C is small, that means you don't really care as much if this cost is large, meaning you will allow a bunch of violations of this inequality, and you will instead try to make this part small. So remember, what happens if this is small? It means that the inverse W, or the margin, is large. It means that the street is wide. Right? So by making C small, it means you'll get a wide street with a lot of points inside the street and maybe on the wrong side of the street. So that's the trade-off. So here's the number of margin violations. What I mean by that is basically margin violation would be some place where this inequality is violated. Okay, if there's no margin violations, that means we know that this cost is 0. And if C is large enough, we will be able to drive this all the way to 0. And we will be able to get exactly the same design of that hard margin classifier. So with linearly separable data and sufficiently large C, this thing is called the soft margin classifier, or support vector classifier. This thing will give us the same exact answer as a hard margin classifier. Okay, but if we use a small value of C, even if our data is linearly separable, it might say, I'm going to focus on making this small, and I'm not going to care as much what happens with this, which means that the street will start to get wide. You will now have a bunch of violations, but that's what you're asking for if you want C to be small. Okay, so let me maybe show you some pictures. So here we have examples with 3 different values of C, and we have our red and blue data, and you can see that the support vectors are the ones that are circled. So those are the ones that are inside the street, or let's say determining the boundary. So when we have a small c, like I was describing just now, we have a wide street. So you can see the boundaries of a street are like over here. I didn't draw those lines perfectly. Sorry about that. Maybe I'll make that one a little bit nicer. Okay. So that's a very wide street, right? And that corresponds to a large margin or a small norm of W. So in this case, because C was small, it said, let's really try to make norm of W small, which made that street wide. And it said, I don't really care if there's a whole bunch of violations or support vectors. So tons of support vectors. At the other extreme, you can see that we have a very narrow street. Now, it's hard to tell exactly, but yeah, it's hard. I don't know, like, if this blue point here is on the wrong side of the boundary. Maybe it is. Might be making an error on that blue point. In any case, you can see the street is very narrow. And then if you look at C equals 10, now we have something in between. So we have something like this. Okay, so by controlling that tunable weight C, we change the width of the street and how many different data points are determining our boundary. Okay, so are there questions on anything here, how that's happening? Yes.
Can you point an optimal C based on customization?
Yes, that's what we're going to do. I'm going to talk about that in just a moment. Before we get to that, I'm just curious if there's any questions, like on how we got here, or anything just mechanically about the derivation. Is everybody good with this? Okay, so this is our. Sorry.
This week's lab, you said that is a derivation that we have to do.
Okay, you're changing topics?
Oh, I was asking if this is relevant.
No, not at all, because the lab is on Unit 6 and this is Unit 7. Right? We're always doing the lab on something we've finished. So we finished Unit 6 last week, and so that lab is on Unit 6. Same with the homework. Okay, so all right, so everybody's good with this support vector classifier. And we said here's how it works. If you have large C, you have a narrow street, small c, wide street. So here's why it matters. Let's think about the bias variance trade-off. So if I have a situation like this on the left, you can see that even though I may have a large data set size, I don't know if this is a couple hundred points or something, you can see that there's only a handful of data points which are actually being used in the design. It's effectively like I have a very small data set that's actually determining my boundary. And as we know, when the data set is small, that means it is very sensitive to variance type issues. If you imagine maybe having some random way of generating this data, and you do this experiment multiple times, you will see your boundary changing significantly every time you do it, because it's really just based on those few points there. So that would have a high variance, whereas this experiment over here, because it's using so many data points, it's going to be quite robust to changes in the data. It gets like an averaging effect. So basically, if you did this experiment over and over again, you would find that your line doesn't really change much at all with different iterations of your experiment. So we have those kind of considerations. So when we have a large C, we have high variance, small c, lower variance. Now let's look at the bias. So when we looked on the left, you could see that we were doing a pretty good job. Maybe one of these blue points was misclassified, but they're all very close or close to being classified correctly, or maybe they are. But look closely at what's happening here. All these red points here are actually misclassified, and all these blue points are misclassified. So the entire boundary has actually tilted clockwise from here to here. So basically this has, you could say, bias issues. There's like just fundamental structural error in that boundary. It's tilted right. So this is the bias variance trade-off. Low bias, high variance when C is large. Low variance, high bias when C is small. Okay, so for a given data set, the way that we would figure out what is the best C is precisely to do cross-validation. K-fold cross-validation, or however you want to do it. Want to figure out what is the right bias variance trade-off for that tunable parameter. Okay, so is that making sense? Okay, one other thing to notice is that, okay, we said that as you increase C, the street narrows, but actually that only happens up to a point, and you can kind of see that here. If I had a very small C, maybe I get my street like this. And as I increase C, my street will get narrower and narrower, but at some point, I will get up to here, and even though I may further increase C, I will never be able to make that street narrower just because of how this is all defined, right? It's defined, at least in this hard margin case, as the minimal, or basically the widest street such that the data is linearly separated. So basically at a certain point, you will find that your street can't it doesn't change. So basically as you vary your C, you will raise it up to a certain point, after which you'll have the minimum number of support vectors, and you'll have no difference in your classifier parameters. So just something to be aware of. When you're playing with things, when you're tuning things, there's a certain kind of maximum C, at which point it doesn't really do you any good to go beyond that. Okay, great. So, okay, any other questions on choice of C? Okay. So now let's relate it to something that we learned about before, which is logistic regression. So notice that if you take this equation here, or this design, I could divide both terms by C without really changing the optimization problem, right? Because if I minimize this, that's the same thing as minimizing that. I'm just scaling the loss. So, and if I do this, then all of a sudden, it looks like I have some sort of loss plus ridge regularization. And so that's exactly what we did over here. And this loss is called the hinge loss. And here is something that looks like ridge regularization. And then if I write my ridge regularized logistic loss, I can actually write it in a very similar form. This is what we might call the logistic loss here. And then we could actually plot this versus this as a function of Zi to see how they differ. Remember, Zi is just the score for the ith sample. And this is what it looks like. So this hinge loss the one we're working with now, once your point is far enough, if it's on the edge of the street or further out, you have a loss of 0. It does not contribute at all to your loss. But once that point is in the street, the loss grows linearly the further more into the street it gets, and then once it gets on the wrong side of the street, it just keeps growing and growing and growing. So that's what happens with this support vector classifier. But our old logistic regression basically has this. So you can see, like, from a high level, they're very similar. They have things that are growing approximately linearly down here, approximately 0 up here, but they do differ in the details. Like this logistic loss never goes exactly to 0 until you're out, all the way out at z equals infinity. Which means that even for those easy to classify points, the logistic loss, or the, cross entropy loss, will basically use those points for its design. So it will get sort of distracted by the easy to classify points, whereas the SVC will not. It will basically, at a certain point, it will say, you're good enough, I'm not going to use you for my design. Okay, so I think this is pretty useful to connect this back to logistic regression, which is something that we spent time studying. Okay, so logistic loss penalizes all samples, whereas this SVC only penalizes the samples that are in the street or on the wrong side of the street. So that's the essential difference, you could say, between these methods. Okay, any questions on this? All right, so just a couple more things to cover. So sometimes when you read about the SVC, it's written in a different way than this is written here. Essentially what they do is they just define a variable for this. And that thing is called the slack variable. So all they're doing is they're replacing this with these xi i's. So there's the slack variables. Right? So they've just replaced this part with xi I. And okay, so they actually have the c over there in this case, but it's not a big deal. And then the other thing they do is, rather than using, so how do they describe this max? Well, if xi I is the max of either 0 or this other thing, then xi I must be simultaneously greater or equal to 0 and greater or equal to this. So that's how they write it. So now this gives a constrained optimization. So here's your unconstrained cost, and then here's your two inequality constraints. So remember that, so it's basically, it's a little bit convoluted because you're designing B and W, which is sort of designing this part of the inequality, which is sort of forcing these guys to react to minimize this. Anyway, it's really just a matter of rewriting it in a slightly different way. But there's actually a nice interpretation to these slack variables. The slack variables just measure how much the margin is violated. So let's say we're talking about these green points. So if a green point is outside the street on the good side of the street, then we know that this value will be negative, and so the slack variable will be 0. If, on the other hand, we have a green point that's inside the street, then the farther it is from this is where we have 0 slack, farther it is this way, the larger and larger that slack grows. Okay, so when it's right on the boundary, when the point is right on the boundary, we know that zi is 0, which means that xi I is going to be 1. Right? When this is 0, then this is max of 0 and 1, which is 1. So as this point moves over here, it's 1. but then it keeps growing linearly. So when it's on this edge, it's 2, and then 3, 4, 5, 6, and so on. Okay, so slack variable 0, we're outside the street on the correct side. Slack variable between 0 and 2, we're in the street. And anytime we're beyond 1, it means that this point is actually going to be misclassified. Wrong side of the decision boundary. Okay. All right. So that's all right. So this is a good time to stop. We'll talk about a couple things with this next time, but implementation. All right. See you guys on Wednesday.